morning. We are going to continue our discussion on the properties of the estimators. Of course, we have kind of talked about most of the aspects, and I said one of the most important aspects is to make confidence statements about the truth, and to that effect we talked about distributions of parameter estimates. What I told you previously was that in order to construct confidence regions for the truth, we always construct confidence regions for the truth. We do not talk about confidence statements for the estimates. There is nothing uncertain in the sense that unless you have made a calculation error for a given data set and for a given estimation method, you can only get one value. What we are not sure about is what the truth is, and we want to provide a region in which we believe the truth falls in. And today we will see how the distribution of the parameter estimate plays a significant role and a critical role in constructing the confidence region. And we talked about central limit theorem as a classic example of a result in deriving the distributions of parameter estimates, but the central limit theorem is useful for linear estimators more or less. When you have nonlinear estimators, then one has to use other methods such as either Monte Carlo simulations or bootstrapping methods. These distributions of parameter estimates that we talk about are also known as sampling distributions. It is said to be the sampling distribution of the theta. Now, often in statistics you will come across a term known as statistic, which is the name of the subject itself, and this statistic is actually defined as some function of the observations. Okay, let me not use F. So any statistic is simply a function of the observations. In that sense, it is no different from an estimator. We have observed many a times that an estimator is also some function of the observations that produces a value which is relevant to a parameter. So, mathematically there is no difference between a statistic and an estimator or an estimate, but there is a very important and a subtle difference, which is that a statistic is any mathematical function that you may construct for your own joy, okay, because you have a lot of time on your hand, you want to do something with your observations, you perform some mathematical operation on it, you will get a number. But on the other hand, when you look at an estimator or an estimate, it is a mathematical operation that you perform on the observations, specifically with the objective of estimating a parameter. So, there is a clear cut objective in constructing this function g when it comes to estimation, whereas in constructing a statistic it could be any function. Obviously, you will not construct any function, but you should remember you will run into these kinds of questions frequently asked on forums as to what is the difference between a statistic and an estimator and so on. That is the prime difference, otherwise both are functions of the observations. So, this term statistic, obviously you would have also heard in the lectures on hypothesis testing, and whatever we are going to discuss today is just a very quick roundup of the detailed exposition that we had in the lectures on hypothesis testing. So, first let us begin with confidence regions. In the lectures on hypothesis testing, I would have gone the other way around. I would have actually explained to you what is hypothesis testing and what are the different approaches, and then proceeded towards constructing confidence intervals. But we will flip the sequence here so that you see that confidence regions here have a larger role to play, right, because the starting point for us has been estimation, whereas in those lectures the focus from lecture 1 has been on hypothesis testing. So, here we are coming from an estimation viewpoint, therefore, we want to conclude that estimation exercise with a confidence statement. essentially constructing confidence regions is very easy provided you know this f of theta hat. Okay. If you know this, then it is just a two-step process for any estimator almost, I mean it does not change much. So, the first step is given f of theta hat, in fact specifically we talk about f of theta hat subscript n, indicating that we have obtained this estimate from n observations. We construct a probabilistic interval, and what we mean by probabilistic interval is we would like to, for example, specify a region in which we believe 95% of the times the estimates would show up, right, and it could be 95%, it could be 99%, you specify that. And generally when you want to construct, for example, a 95% confidence interval, then first you would begin with a 95% probabilistic interval for theta hat, from which you would derive the 95% confidence region for theta. I will just show you the standard example on the mean, but before we do that, an important point to keep in mind in constructing a confidence region is there are two aspects. One is the degree of confidence and the other is the width of the confidence interval. Normally we would like to make a highly confident statement. Ideally we would like to make a 100% confidence statement about the truth, of course, but the unfortunate part is when we attempt to raise the degree of confidence about the region in which we believe the truth is, the interval also widens. We would ideally like to make a highly confident statement and obtain a very narrow interval. Right. Ideally we would like to pinpoint, but that is not possible, but we would like to have as narrow interval as possible, so that the truth is the truth has been captured in as fine way as possible. Unfortunately these are conflicting requirements. As I keep raising the demands of the degree of confidence, the width of the interval also takes a beating. Okay. So, there are many examples that can be given. As I always say, suppose you were to ask what about the students who are absent today. You pick one of the students and you ask, well, where is the student at present? Let us say you happen to be his friend, you would say, yeah, somewhere, now the location is the parameter that you are trying to estimate, and the statement that you would make is, well, he is somewhere on campus, assuming it is a he. And well, that is a confidence statement that you are making, and obviously you cannot state that with 100% certainty, right. So, there is a degree of confidence associated with that statement. If you were to answer make a 100% confidence statement about the location of your friend, then the best answer, that is you can assure that is 100% is somewhere in the universe, right. In fact, you would go on and say either in the form of mass or energy, so that you are completely safe, and then you prove yourself to be an engineer worthy of graduation. Okay, fine, but obviously that is a very practically useless statement. There is no meaning to that. It is so obvious, right. He has to be in the form of mass or energy in the universe somewhere. But what we are looking at is practically useful confidence statements. Now you face the heat when you are required to make 99% or 100% confidence statement, and I would like you to just confine this region to a finite interval. That obviously is not possible. So, you would back off and then say, well, 95%, I am 95% confident that he is somewhere here. But what does that confidence, 95% confidence mean? And we will just go through an example and try to understand what is that 95% confidence mean. So, let us go through this simple example of constructing the confidence interval for mean when you are using sample mean as an estimator. Remember, the confidence region depends on f of theta hat, which in turn depends on theta hat itself. So, this is your starting point from where you would construct f of theta hat, and from where you would actually construct confidence intervals for theta. So, we know that the sample mean follows a Gaussian distribution. Well, for large sample case, regardless of the distribution of the observations, the joint distribution of the observations, and let us assume that we are looking at a white noise process. So, we know that the sample mean follows a Gaussian distribution. In other words, we would say that mu hat or which is let us say x bar or v bar or whatever. So, mu hat, which is nothing but your x bar, follows a Gaussian distribution with mean mu, because it is an unbiased estimator, and variance sigma square over n, very good. Now, generally this is not how the distribution statements are made. As I said yesterday, a lot of times the distribution results are available for large sample sizes. In fact, this is true in general for large sample sizes, that is regardless of the distribution that the observations follow. Therefore, very often you would find a statement that I have shown you on the screen, where we rewrite this and say, well, root n times x bar minus mu over sigma, right, follows a standard Gaussian distribution. Sigma here is the variability of the process, and that is a very important point to observe. That is, normally statements on distribution are in terms of root n times, for example, you would find in general root n of theta n, theta hat n minus theta naught or theta. Distribution statements are made for this quantity rather than theta hat. Although we keep saying that we want f of theta hat, right, but this is the case, and the reason is, if you look at this statement here, obviously as n goes to 0, we have already seen that sample mean is a consistent estimator, or it is anyway unbiased and its variance shrinks to 0. When n goes to infinity and the random variable acquires a variance of 0, it ceases to be a random variable. So, it becomes a deterministic quantity. Therefore, it does not make sense to talk about its distribution, right. Distribution statements are made for variables that are random, not for deterministic variables. On the other hand, if you look at this parameter here, that is root n times x bar minus mu by sigma, its variance does not die down to 0 as n goes to infinity. It remains a random variable. So, that is the difference between giving distribution statements for theta hat alone and a standardized theta hat. In this case, the standardization is this. Okay. In some other case, the standardization would be with respect to something else, but always you would see the standardization being made with respect to the truth and with a denominator that has got to do with the variability of the theta hat. So, to summarize, distributional statements are always made in terms of root n times theta hat minus theta n, theta naught by something. If it is if theta hat has a Gaussian distribution, if it has some other distribution, some other standardization, but the root n appears in so that the standardized random parameter estimate remains a random variable. Clear? Any question on it? You are okay? Fine. If you have any question, you should actually ask it now. Now, in confidence region construction and in hypothesis testing, we work usually with standardized statistic rather than the plain statistic or estimate. So, let us now go ahead and construct the confidence region for mean when we use sample mean as an estimator. In other words, if you use median, a sample median or some other estimator or weighted mean and so on, you should come back to this step 1 where you come back to f of theta hat n, so that your probability interval is properly set up. So, we know that for a standard Gaussian distribution, the 95% probability region for that random variable is plus or minus 1.96, and that is the statement there is nothing new there. But what we are doing is we are now constructing a confidence region from this probability region. So, we are turning the tables around. First we say that this is the confidence region for the standardized statistic, and now we say the focus is on the truth theta naught, which is in this case mu y, right. Of course, I have used x on the board, but it is okay, you should be able to follow. So, I have here the my interest is on saying something about mu y. I have already computed y bar. I am assuming that I know sigma y. So, the only unknown is mu y, and clearly this says that I cannot pinpoint mu y from y bar, and as a result I construct this confidence statement. So, you must ask yourself, and I must have talked about this in the video lectures as well, as to why we now change the term from probabilistic interval to confidence region. Why is that? Let us see if you have really listened to the video, and why do we not use the term, same term as we move on to mu? Yes.
We say it's confidence and not probability because mu y is a not random variable, it's a parallel.
Good. So, it is a deterministic variable, it is a deterministic quantity. Therefore, it does not make sense to say with 95% probability mu is between this. Although my knowledge has uncertainty, that has got nothing to do with the mu. That is the philosophy in classical estimation. Whereas in Bayesian estimation, I say that my knowledge is uncertain about the truth. Therefore, I will begin by assuming the truth itself is random. That is the difference. Okay. Because the true parameter, that is theta naught, is a deterministic quantity, we use the term confidence, and also there is another reason which is related, of course. Suppose you were to follow this procedure in practice, of course you will end up with that interval y bar plus or minus 1.96 times sigma by root n. That interval is a guess for your mu, and by saying that you are 95% confident, now comes the interpretation. What you are implying is, if I were to run, for example, 1000 simulations, if I had 1000 realizations of the data, each realization would give me y bar, and from each y bar I would construct one interval, this kind of an interval. Out of this 1000 realizations, roughly 9, remember you have 1000 intervals now, right. Out of this 1000 intervals, 950 intervals would have captured the truth and 50 would have missed out the truth. And if your Rasi of the day is not so great, then you may run into that realization which gives you that interval that does not contain the truth. Okay. But it says the probability of missing out on the truth in your interval is 5%. It does not say that the probability that the truth does not reside in that interval, it does not say that. It says the probability of you missing out on the truth in that interval is 5%. So, that is the interpretation of 95% confidence interval. Let me just show you here exactly what I did. I simulated what I just said exactly. I generated 1000 different realizations, each realization containing 1000 observations, and then I have y bar constructed from each of those 1000 realizations. Corresponding to each y bar, I have an interval using that formula, assuming that I know sigma. It is a very simple case, but it is okay. It serves to illustrate just serves the purpose. Now, what I am showing you on the screen are those intervals which have failed to capture the truth. Because this is a simulation, I know the truth is 0, and you can see I am showing you the end points of the interval, and 0 is in the middle here, right. You can see that these intervals are either completely to the left or to the right, which means they have missed out capturing the truth. That count, if you were to count such intervals, they turn out to be 51, obviously because I have only simulated 1000 realizations. This number, this is now 0.051, right. But if you were to now extend this simulation to many more realizations, it gets better and better and goes to 0.05. These are 95% confidence intervals. So, now hopefully you understand what is the meaning of 95% confidence. 99% confidence interval would mean that you would have how many such intervals that miss out the truth in 1000 realizations? 10. and you should do that. You should go back, just it is a very simple exercise. You should just go and do it for yourself, so that you are convinced that you understand this concept very well, right. But of course, what would happen is, when you go to the 99% confidence problem, the interval becomes wider. So obviously, as the interval is getting wider, the probability of missing out on the truth, it is like you are casting a net like a fisherman, and the degree of confidence is raising the width of the net, the size of the net. So obviously, you would be able to, the probability that you will be able to capture the truth is increasing, and as you go up and up, it will the probability of missing out on the truth would come down. So this is what is confidence region for you. What so therefore, when you estimate any parameter, there is a certain procedure. You choose an estimator, and you should know the distribution of that estimate, from where you should be able to construct the confidence region. You should not just report a point estimate and say, I am done. You asked me for a point estimate, the estimate I gave you. That is only half job done. You should report the confidence region. Typically, what one does is first calculates the variance, that is your sigma theta hat, not sigma y, sigma theta hat, and reports a standard error. That is what you would see in many of your ARIMA models. If you have estimated, the estimates are reported along with the standard errors, correct. Those standard errors are nothing but sigma theta hat. From the sigma theta hat, if you assume theta hat follows a Gaussian distribution, then the confidence region would be 95% confidence region would be simply theta hat plus 1 plus or minus 1.96 sigma theta hat. You may wonder, where is the root n gone, but that has gone into your sigma theta hat. The root n appeared in this expression because you have sigma y, right. So if you know that theta hat follows a Gaussian distribution, most of the times the model parameters that you are obtaining, that is whether it is of AR or MA or ARMA and so on, all of them asymptotically follow a Gaussian distribution, and you should construct this confidence region. What is the purpose of constructing this confidence region? It is twofold. One, you are telling me, you are giving me an interval in which the truth is, and if you have done a good job, then it should have actually captured the truth. But there is a chance, I know 5% chance that you would have missed out on the truth, right. But I would have done my homework to make sure that I do not give you that kind of a realization, right. So, so that you know I do not realize it later on, I just make sure that you have a realization which will give you an interval that captures the truth. The second purpose of confidence region is in hypothesis testing, okay, and which I will show you very quickly. So the next 5 minutes or 7 minutes we will review hypothesis testing, and then we will move on. These are some of the confidence intervals for some of the other estimation exercises. For example, just now we assume that the sample size is large and sigma is known. If that is not the case, that is you have small sample size, let us say the observations are falling out of a Gaussian distribution, but the variance is unknown. Then, as you know from statistics, somewhere you must have heard something called a t distribution. In that case, the confidence interval changes slightly, where you replace this 1.96, that number, for 95%. Although it says with 95% confidence, I have used the generic symbol alpha. You should set alpha to be 0.05 there in the statement. The t alpha by 2 in bracket n minus 1 denotes the quantile in the t chart or in the t distribution of n minus 1 degrees of freedom, and alpha by 2 corresponds to the quantile there, that is your probability there. You are looking at the left side probability of it. The t distribution looks pretty much like a Gaussian, except that it does not have as flat a tail as a Gaussian one. In fact, as n grows large, you would actually use basically, it should not read sigma hat y there, it should read sigma hat theta. There is a mistake there, I would say. So as n grows very large, t distribution tends to Gaussian distribution. So you should not be even worried of a t distribution when n is very large, even though the variance is unknown. So, these are some standard results from statistics, very well known for decades, and one can construct what are also known as one sided confidence regions. That is, you can ask, and this may be required in hypothesis testing, where you give a lower bound and an upper bound depending on what you are interested in. For in 53 I have given equation 53, I have given the confidence region for the variance. If you use the unbiased estimator of the variance, you have to be careful here. We are assuming that we are using an unbiased estimator of the variance. Of course, as n grows very large, then it does not matter whether you are using unbiased or biased estimator. Whereas in 54 we give what are known as one sided confidence regions, all right, and those are useful in conducting hypothesis tests which are called one sided or lower tailed or upper tailed hypothesis tests.